So if you haven't watched the previous questions about dimensional analysis, it would be a good idea to watch those first because these ones are more complex. It says complete the following unit conversions. Be sure to use dimensional analysis and show work. The quiz may ask questions about how the dimensional analysis is set up. So essentially none of these questions are really chemistry, but learning how to set up dimensional analysis is extremely important for chemistry, especially the first 4 chapters of General Chemistry 1. And the material in the first 4 chapters of General Chemistry 1 shows up in pretty much every chemistry class. So it's really important to learn these concepts. So we're going to start with the dimensional analysis. So we have 0.00250 meters cubed to centimeters cubed, and it gives us some possible information. 1 meter equals 100 centimeters. But there's a problem. The problem is this is meters cubed, a unit of volume, and this is centimeters cubed. A centimeter cubed is a cc, and like the healthcare industry or something like that, and it's a milliliter. This is the same as a milliliter. A meter cubed, a meter is much longer than a centimeter, and a meter cubed is a unit of volume that maybe an engineer designing a building would use, but it's certainly not, how much they're going to inject into a patient, right? You're not going to inject meters cubed of solvent. So, or medicine, but you would do centimeters cubed or milliliters. So we have this possibly useful information. Again, the problem is this is meters cubed, and this is meters, this is centimeters cubed, and this is centimeters. How do we fix that? It turns out it's actually pretty easy to fix that. All we have to do is take this and cube it, and take this and cube it. And they'll still be equal because we cubed both sides. So as long as we do the same thing to both sides, it works. Well, 1 meter cubed is easy because 1 times 1 times 1, said another way, 1 cubed is just 1. So it's 1 meter cubed equals, the 100 centimeters is a little harder. It's not hard, but you could either cube it in your calculator or just do 100 times 100 times 100. And it turns out that that's a million. A million in scientific notation is 1 times 10 to the 6th centimeters cubed. Since these are both metric units, meters and centimeters, this is an exact definition. There's no sig figs in this. Said another way, our answer should have 3 sig figs, 1, 2, 3, because our original measurement has 3. We don't have to worry about the significant figures in this because it's an exact equality. All right, so now we're going to take this number, which is 0.00250 meters cubed, times. We need to turn this equality into a conversion factor. And as we've done before, to turn equalities into conversion factors, we're going to write 1 on the top and 1 on the bottom. Well, how do we decide which one goes on the bottom? Well, we want the 1 on the bottom that's going to cancel out the meters cubed. So in this case, we want to put the 1 meter cubed on the bottom and the 1 times 10 to the 6th centimeters cubed on the top. Multiply by the top, divide by the bottom. When you do that, you're going to get, in your calculator, 2,500 centimeters cubed. Since this kind of has 2 sig figs, and it's kind of ambiguous about how many significant figures it has, you're better off to write this in scientific notation. So move the decimal place over 3 times, and you get 2.50 times 10 to the 3rd. That does have a centimeter. Centimeters cubed. Okay, so it's 2.50 times 10 to the 3rd. Centimeter cubed is probably the best answer because this has 3 sig figs and this has 3 sig figs. So this example has a little bit of a real world kind of feel to it. It says a car traveling between Albany and New York City averages 71.4 miles per hour. If it takes the driver 2.2 hours to make the trip, how many kilometers were driven? And then it gives us the equality between miles and kilometers. Now, when we're looking at a question like this, it's now a multi-step conversion. Okay, we're starting with 2.2 hours to make the trip, and we want to know how many kilometers of distance were driven. There's no equality here between kilometers and hours, so we can't make this in one step. When you have to make it in more than one step, what I suggest doing is kind of a plan of attack, okay? And in this case, we're starting with the 2.20 hours, so we want to convert from hours to what? Well, we want to convert from hours to how far this person is driving in miles. So we want to convert those hours to miles. Then once we have miles, we can convert to kilometers. Okay, so it's a two-step process like this. Note that for every arrow, we need a conversion factor. And the miles to kilometers equality is here. So conversion factors come from equalities. And we have an equality between miles and kilometers, so we can make a conversion factor for this conversion. But we don't have an equality between hours and miles. But actually we do, because we have 71.4 miles per hour. And what this means is that for every 71.4 miles that this person drives, it will equal 1 hour of their time. So miles per hour means per 1 hour. So the equality is 71.4 miles equals 1 hour. This comes up in chemistry a lot. We have units like molar mass, which is grams per mole. It's grams per 1 mole. We have units like molarity, which is moles per liter, moles per 1 liter. So miles per hour, miles per 1 hour. So this is the equality. So now we have an equality to make this conversion, and we have an equality to make this conversion. Let's set it up. We have 2.20 hours times. For the first conversion between hours and miles, we want to use the relationship between miles and hours, not surprisingly. We want hours to cancel out. So where are we going to put it? We're going to put the 1 hour on the bottom. And on the top, we're going to put the other one, which is the 71.4 miles times. Now, we want to convert these miles, because hours are gone, into kilometers. Turns out the question gave us that equality, which is right here. In this case, we have this unit. We want to get rid of these miles, so we put the 1 mile on the bottom and the 1.609 kilometers on the top. Now, if we look here, this has 3 sig figs, this has 3, this has 4. Our answer should have 3 significant figures. And when you do all this math, you get 253 kilometers were driven by this person in the 2.2 hours. The final question here says, a ball is traveling at 30.6 meters per second. What is the speed of the ball in miles per hour? So in this case, we have 2 equalities to help us. We know that 1 mile is 1609 meters and 1 hour is 3600 seconds. But the difference here is that where we have the units. So what this means is that this is moving at 30.6 meters per 1 second. So we can think about it this way. And in this case, we want to change both the meters to miles, because we want miles per hour. So we want miles over hours. So we want to change the meters on the top to miles, and we want to change the seconds on the bottom to hours. So we need to convert both of them. But we have to be a little bit more careful about what goes on the top and what goes on the bottom, because in this case, we're converting both the top and the bottom. Now, it turns out it doesn't really matter which one we convert first. I'm going to convert the meters to miles first and then the seconds to hours. But if you wanted to convert the seconds to hours first and then the meters to miles second, it doesn't make any difference. Okay, so let's do that. We have meters here, and we want to cancel that out and end up with miles on the top. So if we use this equality that we already have, we want to put the 1609 meters on the bottom, so the meters will cancel out. We want to put the 1 mile on the top, so now we have miles on the top, and that's what we want. Now for the second conversion, we have to be extra careful. And the reason we have to be extra careful is simply because it's less familiar. In all the previous examples, I don't know how many questions we did, 10 or something like that, okay, we were canceling out units on the top. So we're familiar with that. We're less familiar with canceling units on the bottom, so we have to be a little bit more careful. So in this case, we have 1 hour equals 3600 seconds. Note that seconds are on the bottom, and what I want is hours on the bottom. Well, if seconds are already on the bottom, I want them to cancel out from the bottom. Said another way, I want to put it on the top. So I put the 3600 seconds on the top, so now it'll cancel out with those seconds that are on the bottom, which again is different than what we've done before. The rest is the same though. Once I decided to put 3600 seconds on the top, I automatically decide to put the 1 hour on the bottom because I'm using this equality. Multiply through by the tops, divide by the bottoms one at a time, and when you do that math, you get 68.5 miles per hour, or is abbreviated mph, is another way of putting it, but I'm just going to write it this way. Okay, notice this is 3 sig figs, this is 4, this is an exact equality. 1 hour is exactly 3,600 seconds. There's no uncertainty in there. That's not a measurement. So 3 and 4, my answer should have 3. And that's how we would do it right here. Again, dimensional analysis is extremely important in chemistry classes. So learning this process, or the process of all of these, is way more important than finding the answer. I understand you could just type these numbers into your calculators and get the answer. I also understand that you could just put these into Google and it will tell you the conversion. It's not about learning the conversion itself. It's about learning this process. Because in chemistry, there are things that Google will not be able to tell you, but this process will allow you to solve.